Okay, so this is our 11th example from our derivatives of functions involving logarithmic functions. We've got f of x equals the natural log of the absolute value of cosine of x divided by cosine of x plus 1. Since we've got this function inside the logarithm, the first thing that we need to do to have some sense of what this graph looks like is to look at the argument function. So we're looking at the function inside those absolute value bars. And once we know how that function behaves from negative infinity to infinity, we can use that combined with what we know about the graph of the natural log of x to infer what this graph has to look like. So I've got g of x is cosine of x divided by cosine of x plus 1. Now we're going to have vertical asymptotes whenever the denominator is 0 and the numerator is non-zero. Since the numerator and denominator are basically the same function, except we've added 1 in that denominator, there's no way that these can be 0 at the same time. That's like saying like x is 0 and x plus 1 is 0. Like they can't both be 0, not at the same time, unless, we're taking a product or something like that. Anyway, so I don't have to worry about the possibility of cosine of x and cosine of x plus 1 being 0 at the same time. So we're going to have vertical asymptotes then when the denominator is 0, the numerator is automatically non-zero at that point. And then we'll have zeros of the function whenever the cosine of x is 0. So we just graph y equals cosine of x. We see that the cosine of x is 0 at pi over 2 and 3 pi over 2 and 5 pi over 2 and 7 pi over 2. So this original function, or this, not the original function, g of x is going to be equal to 0 at all of those odd multiples of pi over 2. So we can plot some points. We'll evaluate at, let's start with negative pi over 2. Label that point. And so we'll have g is equal to 0 there. And we'll just sort of copy and paste that code. Label some of the other zeros. So negative pi over 2, then pi over 2. I think I want them all to be orange. So at pi over 2, we're going to get a 0. Then at 3 pi over 2, we'll have a 0. Again, all those odd multiples of pi over 2. You can go ahead and erase it. Honestly, okay, not that, try to fix it. If you make big things on the C. Everything's one. What you probably want to do is and we just continue in this way. Now we also have those vertical asymptotes whenever cosine of x plus 1 is equal to 0. So our cosine graph, we can see it here. We know that cosine of x plus 1 equals 0 and cosine of x equals -1. That cosine function is equal to -1 at pi. And then because that function repeats, we can add 2 pi as many times as we want. We can subtract 2 pi as many times as we want. And we'll also have asymptotes there as well. Those have already been graphed. This one is x equals pi. This is x equals pi minus 2 pi, which is negative pi. Then we've got x equals 3 pi, x equals 5 pi, x equals 7 pi, and so on. So that's where our g of x graph has asymptotes. Now, in order to figure out what the graph of g should actually look like, we should look at the cosine of x and the cosine of x plus 1 graphs at the same time. Okay, so those are our two graphs. And this, we're taking the values of the teal graph and then we're dividing by the values of this white graph. So as we approach these asymptotes, like let's say just this one at x equals pi, what we have is -1 divided by a tiny positive number. -1 divided by a tiny positive number is a large positive, -1 divided by a tiny positive number is going to be a large in magnitude negative number. So our function is going to approach negative infinity on either side of pi, and that's going to happen at all of those vertical asymptotes. And then at, let's say x equals 0, what we have is cosine of 0, which is 0, or excuse me, cosine of 0, which is 1, divided by a cosine of 0 plus 1, so that's 1 plus 1, which is 2. So the y value on the graph of g of x should be 1/2, and this y value is 1, so it's going to be half of the size of that y value. So our g of x graph should look almost like a parabola on each little branch here, with a maximum at 1/2, and then it's going to approach negative infinity as it approaches those vertical asymptotes on the left and the right. So let's look at the graph of g. That's what we see. The y value at 0 is 1/2, and we have the same y value at 2 pi, 4 pi, 6 pi, and so on. And then the function g approaches negative infinity as we approach those asymptotes. Now remember, whoa, I didn't mean to do that. I don't know how that happened, but it must have accidentally did that. So we're right here now. That was bizarre. I wonder what happened there. Now we want to not just look at g of x. We're not just taking the natural log of g of x, because we'd actually have a problem with that, right? Because we can only take the natural log of a positive number. But that's fine, because we're actually not asked to take the natural log of g of x. We're asked to take the natural log of the absolute value of g of x. So the absolute value of g of x is going to look very similar to this. It's going to be exactly the same as this function here when the function is positive, but when that function is negative, which is like right there and right there, we're going to multiply those values by -1. So we're going to see something that looks like roughly like this. Now let's look at the g of x, absolute value of g of x graph. It's basically going to take all those y values below the x-axis and it's going to flip them up. All right. So that is what we're actually taking the natural log of. I'd like to get rid of that g of x graph now, because let's just look at the absolute value of g of x instead. So that's what we're looking at. Now, when we take the natural log of something, remember what y equals the natural log of x looks like. Let me get rid of that cosine of x code. Let's look at natural log of x. Can you see it? Did it graph it? Natural log of x looks like that. So many asymptotes and the graph of the absolute value of g of x in the way, so it's a little bit difficult to see. But just try to focus on that purple graph for a moment. That's natural log of x as x approaches 0 from the right. So as what we put into the logarithmic function is a tiny positive number. The y values are large in magnitude, but they're negative numbers. And as x goes to positive infinity, so that's what's inside the logarithm goes to positive infinity, the y values go to positive infinity, but they go to positive infinity very, very slowly, because the graph or the derivative of natural log of x is just 1 over x. So if you plug in x equals 100, the derivative of natural log of x at x equals 100 is 1/100th. So the slope is tiny, positive, but tiny, and it's growing. It's growing slower and slower as x gets larger and larger. But it continues to grow. It continues to go to infinity as x goes to infinity. So with that in mind, let's think about what the log of the absolute value of g of x should look like. I'm going to get rid of this log of x and think about the log of g of x. Well, whenever g of x goes to infinity, and it goes to infinity at all of these multiples of pi, right? We're taking the log of the absolute value of g of x. So as the absolute value of g of x goes to infinity, the log should also go to infinity. So where g of x has these vertical asymptotes at all those odd multiples of pi, the natural log of the absolute value of g of x should also approach infinity at those odd multiples of pi. Now, as g of x approaches 0, or as the absolute value of g of x approaches 0, so at those odd multiples of pi over 2, we have all of those zeros of the g of x function. Then we're taking the logarithm of a tiny positive number. And the log of a tiny positive number is a large magnitude negative number. So I would imagine that our function is going to have asymptotes at all of those odd multiples of pi over 2. and the function is going to go to negative infinity at all of the zeros of that g of x function. So that's our thought. So that means I need to graph some of those asymptotes for those odd multiples of pi over 2. So I'm doing that here. I'm going to graph those in orange. So you see that that trend continues. Let's just go from negative pi to, let's just say 7 pi is sufficient, I think. All right, so our graph looks like that. Now our function should, our original function should approach negative infinity as it approaches these asymptotes, these orange asymptotes, from the left and the right. So the function approaches positive infinity as we approach these white asymptotes, negative infinity as we approach the orange asymptotes. And then at the even multiples of pi, so 0, 2 pi, 4 pi, 6 pi, and so on. Well, we're just going to take the log of this number, like it's 0.5. G evaluated at 0 was 0.5. So we're going to have the natural log of 1/2, or -1 times the natural log of 2, which is about negative 0.69, I think, approximately. So our function will be negative 0.69, which is this natural log of 1/2, which is natural log of 1, which is 0, minus natural log of 2. So we get that negative natural log of 2 for the function at 0. Actually, let me just evaluate this at 0 and see what we get. It says I've defined f in more than one place. I'm just going to call it new. Let's evaluate f new at 0. So I get that negative 0.69. I claim that negative natural log of 2 is the same as that, which is the same as natural log of 1 minus natural log of 2, which is the same as natural log of 1/2. See, they're all the same value. I prefer the simplified form, negative natural log of 2. So that is our function value there. And then the function f should approach negative infinity as we approach those orange lines. And then positive infinity as we approach the white horizontal, or excuse me, vertical lines, vertical asymptotes. So this is my graph. I want to get rid of the graph of the absolute value of g of x now. And that is roughly what our graph looks like. And maybe we'll just let our y values go from -8 to 8. Now it looks a little funny, but that is the trend that we expected. The function is going to positive infinity there at all the odd multiples of pi. It goes to negative infinity at the odd multiples of pi over 2. It's equal to that negative natural log of 2 at 0, 2 pi, 4 pi, 6 pi, and so on. So that is our function. And we still have those points plotted. Those were the zeros of the absolute value of g of x. We don't really need those anymore. So I will ask Desmos to stop plotting them now. All right, and that is what we got for the graph of f without even taking a derivative. We know that the function looks like this based entirely on the graph of g of x, graph of the absolute value of g of x, and then what we know about the natural log function as its argument approaches 0 from the right and as its argument goes to infinity. So we didn't even have to take a derivative to get this much information about f of x. It's actually very similar to what I drew on my paper. Actually, I want to show you what I drew on my paper. So when I drew this on my paper, this is what I got. And it's very, very similar, right? It's a little bit difficult to see. There's like weird shadows in Starbucks right now. But that's very similar to what we have on Desmos. My functions don't get as close to the asymptotes as the functions on Desmos do. But we still have those sort of U-shaped things here. And then we have the function that's approaching infinity at all the odd multiples of pi, and then negative infinity at all the odd multiples of pi over 2. Now that we've examined the argument and its absolute value, and then taken the log of that and inferred some limits, let's evaluate the derivative and see what the derivative looks like. Okay. So we're taking the derivative with respect to x of the natural log of the absolute value of cosine of x divided by cosine of x plus 1. And we know, I'll just do the calculations here in line. We know that the derivative of log of a function is 1 divided by the function. So I'm going to have 1 divided by this fraction, and dividing by a fraction is the same as multiplying by the reciprocal. So I'm going to get cosine of x plus 1 divided by cosine of x, right? Because I have 1 divided by this is this, times the derivative of the inside by the chain rule. And the derivative of the inside is that cosine of x divided by cosine of x plus 1. I skipped a step there, but I think you guys all know what I just did. I did 1 divided by a fraction. It's a reciprocal of that fraction, so I just flipped it. Then you say, okay, well, what's the derivative of this quotient now? Well, according to the quotient rule, it should be the bottom function. Let me just, hold on, let's rewrite this. Cosine of x plus 1 divided by cosine of x. And then we're going to multiply by a fraction. And the fraction is low d high. So the bottom function times the derivative of the top function, that's negative sine of x, minus pi, which in this case is cosine of x, d low, derivative of cosine of x plus 1 is negative sine of x, plus 0, which is just negative sine of x, all divided by low. So that's cosine of x plus 1, quantity squared. Now, if we try to simplify this, imagine you've got brackets here and here. This cosine of x plus 1 and one of those cosine of x plus 1s will reduce. So I can delete that as long as I change that exponent to just a 1. I can put this cosine of x in this denominator if we just multiply straight across, right? And so that is our derivative. Now we want to simplify further. So if we distribute that negative sine of x here, we're going to have negative sine of x times cosine of x. And then if we distribute the negative sine of x to the 1, we're going to have a negative sine of x there. And then we'll have a negative cosine times a negative sine is going to be a positive sine of x times cosine of x. And when you see that, you see the negative sine of x cosine of x and the positive sine of x cosine of x reduce. They just add to 0, right? So we just end up with a negative sine of x in the numerator divided by this cosine of x times cosine of x plus 1. So that is our first derivative. After applying the chain rule with the quotient rule and then simplifying. They want parentheses around cosine of x. That looks like that. Oh my goodness, that is a mess, isn't it? Let's get rid of the graph of our function f and see if it's similar to the function that I graphed on paper. So I think that is very similar to what I graphed on paper. Let me see if it's what I graphed on paper. So this is what I graphed on paper. I said my function for f prime was this negative sine of x divided by cosine of x times cosine of x plus 1. We'll have zeros whenever the numerator is 0 and the denominator is non-zero. Sine of x is 0 at all of the multiples of pi, so 0, pi, 2 pi, 3 pi, 4 pi, and negative pi, negative 2 pi, negative 3 pi, and so on. And the denominator is non-zero, or this cosine of x is non-zero with its values, but cosine of x plus 1 is equal to 0 when x equals pi. So this denominator will be 0 at pi plus 2 pi n. We can add 2 pi as many times as we want, but the numerator is also 0 at the same time. So that's a 0 over 0 indeterminate form at all of those odd multiples of pi. But the even multiples of pi, our numerator is 0 and our denominator is not. So we would expect our derivative function to have zeros at all those even multiples of pi. So we'll have a 0 there and a 0 there and a 0 there. And then this cosine of x is 0 at all of the odd multiples of pi over 2. So we're going to have something that's non-zero divided by something that's 0 times just a 1 in that case. And what we get if we look at the limiting values as we approach those odd multiples of pi over 2. Well, actually, those are a bunch of calculations I did on a separate sheet of paper. But we get negative infinity from one side and positive infinity from the other. Let's see, maybe we should actually do that calculation again. So I've got the limit as x approaches pi over 2 plus 2n plus 1, so we're at odd multiples of pi over 2 of sine, or negative sine of x, excuse me, divided by cosine of x times the quantity 2 cosine of x plus 1. This is approaching 0. This is positive 1 for some of the multiples of pi over 2. And negative 1 for other multiples of pi over 2, because we know that sine is equal to 1 at pi over 2, and it's equal to negative 1 at 3 pi over 2. So when I'm thinking about this limit, but we're going to have different behavior at pi over 2 than we do at 3 pi over 2. So rather than doing this, I'll compute this. Let's look at the limit as x approaches pi over 2 plus 2 pi n. Then our sine value is equal to 1. So we're going to have 1 times a negative. It's going to give us a negative 1 in the numerator. And this is going to approach 1. So I'll have negative 1, a 1, and then the cosine of x is approaching 0. So I need to look at that cosine of x. Now, the values of the cosine graph are different from the left and the right. They're all approaching 0, but as we approach pi over 2 from the left, the cosine values are tiny positive numbers. So I will look at the limit from the left separate from the limit from the right. This is a negative 1 divided by a tiny positive number to the left of our pi over 2 times 1. Negative divided by a tiny positive number is going to be a large in magnitude negative number. So our function should approach negative infinity as we approach pi over 2 from the left. And then as we approach pi over 2 from the right, going to be very similar. We still have that negative 1 in the numerator. But now instead of dividing by a tiny positive number, we're on the right of pi over 2, we're dividing by a tiny negative number. So this is a negative divided by a tiny negative number. Negative divided by a negative is a positive. And dividing by a very small number is the same as multiplying by a very large number. So we're going to go to infinity. Okay, so we know on the left and right of pi over 2, we get negative infinity and infinity. This is in the graph of f prime. So we have negative infinity on one side of pi over 2 and positive infinity on the other. All right. And then at 3 pi over 2, we're going to have slightly different behavior. We'll approach from the left and the right. So our sine function is going to be -1 there. So if negative times a negative is a positive 1. And then this is approaching 0. And then this is 0 plus 1, so it's just a 1. So the sign of this quotient is determined by the sign of that tiny positive number. So if we're on the left of 3 pi over 2, that means we're right there. Those are going to be tiny negative numbers to the left of pi over 2. 1 divided by a tiny negative number is a large negative number.
So now where's that third?
So we're going to approach negative infinity to the left of 3 pi over 2. And then to the right of 3 pi over 2, we're going to be dividing by a tiny positive number.
Yes, exactly. So x is the shortest side. Your back is the shortest side. So it's the smallest number, which is 30. So 30%. So
I have a positive infinity on this side. All right. And then what else did we say? This is f prime.
The original formula for this x. So with that, all you do is like you plug in the x for 30%. Right.
Now this is 0 when the numerator is 0 and the denominator is not. We said that that numerator is 0 at all of the multiples of pi, but we have to exclude, I keep writing 2 cosine of x plus 1, but I think that that's incorrect. I think that's just supposed to be cosine of x plus 1. Sorry about that. I don't know why I wrote an extra 2 there. So this will equal 0 whenever sine of x is 0 and the denominator is non-zero. But this is also 0 at x equals pi, because cosine of pi is -1. -1 plus 1 is 0. So we'd have a 0 divided by 0 indeterminate form at all of those multiples, or at pi plus 2 pi n. So at all of the odd multiples of pi, we have a 0 over 0 indeterminate form. But at the even multiples of pi, we just get 0. So our graph is going to look roughly like this. At 0, the derivative is 0. At 2 pi, the derivative is 0. Oops, that's not right. At 3 pi, that's one of those 0 over 0 indeterminate forms. Then at 4 pi, we'll have 0 again. So 0, 2 pi, 4 pi, and so on. We'll get zeros. Okay. All right. So now we have to think about what happens in the vicinity of pi. Because at pi, we've got that 0 over 0 indeterminate form. Let's take the limit as x approaches pi. Plus 2 pi n, and if we factor out that pi, we've got pi times 2 pi n. We have negative sine of x divided by cosine of x times cosine of x plus 1. And that's a 0 over 0 indeterminate form.
Okay.
So we can use L'Hopital's rule for that. So we'll take this limit of this expression is equal to the limit of this expression. Take the derivative of the numerator, which is negative cosine of x, and you divide by the derivative of the denominator. If you want to, you can use the product rule. You don't have to do that. If we use the product rule, we'll have the following. We have the derivative of the first, derivative of cosine is negative sine of x, times the second, plus the derivative of the second, which is negative sine of x as well, times the first. And so I have the limit as x approaches pi times 2n plus 1 of this expression. And we see that this expression and this expression have a negative negative sine of x in common, so we can factor that out. And then we have negative sine of x times cosine of x plus 1 for that first term. And then negative sine of x times a cosine of x for that second one, so we get 2 of those. I see where that 2 came from. I don't know why. I guess I was sort of thinking of this calculation somehow. It's because I've done the calculations before. I accidentally did this whole lecture and I didn't record it. So we're redoing it. So we've got this. Negative divided by negative is positive. And then you say, okay, well, what happens at pi, essentially? Well, the numerator is cosine of pi, which is -1. Sine of pi is 0. And then this is -1 times 2 plus 1. So -2 plus 1 is -1. So we end up with this -1 divided by -1, which just cancels. You just get a positive 1 divided by 0. So you have a 1 over 0, which either gives us plus or minus infinity. And you can determine whether it's plus or minus infinity depending on the SIGN sign of that sine of x as we approach pi. So I'll look at that sine of x graph again. We're approaching pi from the left and from the right, and we're going to have different behavior. The sine function is positive to the left of pi and negative to the right of pi. So when we evaluate that limit as x approaches pi from the left, we're dividing by a tiny positive number. So this is going to be a large positive number when we divide. 1 divided by a tiny positive number is a large positive number. And then as we approach the same asymptote from the other side, we've got 1 divided by a tiny negative number. 1 divided by a tiny negative number is a large negative number. And so we get negative infinity as we approach from the right. So each of those 0 over 0 indeterminate forms, which is an odd multiple of pi, corresponds to a vertical asymptote. And we approach positive infinity to the left of that, on the left of that asymptote, and negative infinity to the right. So I'm going to draw those asymptotes in pink. So we're going to go to positive infinity to the left, and then negative infinity to the right.
Not based on.
And of course, these patterns repeat. Now we know that the function is 0 here, so I'm just going to extend that graph. And then it repeats every 2 pi. Now at pi over 2, our function goes to negative infinity to the left and positive infinity to the right. So I have negative infinity to the left and positive infinity to the right here. And then at pi and 3 pi over 2, the function values are both going to at negative infinity as we approach pi from the right and negative or 3 pi over 2 from the left. Now, I don't know what the function values are. I know we're going to have a minimum function value on this interval from negative pi over 2, or sorry, from pi over 2 to pi. We should have a maximum function value from pi to 3 pi over 2. And then that pattern should repeat here and here. Now, I don't know exactly what that looks like. When I did this, I plotted a point and I evaluated it, and this is kind of what I got. I don't know if that's accurate. Let's look at desmos.com and see what the derivative looks like now and see if that's consistent with our picture. This was the picture I drew the first time. And this is the picture I drew the second time. I didn't plot a point in between, but we could plot a point in between to sort of guess what the function looks like in between those asymptotes. I think this is similar to what I had, but the minimum value that I was imagining and the maximum value for this on this branch that I was imagining, it wasn't 3.33 and negative 3.33. And I'm not actually sure what x value that is. It's not at 3 pi over 4. It's a little bit to the right, or excuse me, a little bit to the left of that 3 pi over 4. So I'm not really sure where that derivative, the second derivative would be 0. But this is the derivative graph. It had consistent with what we drew on paper, although I had my minimum and maximum values wrong on those branches where the function has minimum and maximum values. But let's compare that to the graph of the original function and see if it's giving us a slope that seems, consistent with what we see in the graph of the function. So here's the original function. And let's just look at it on the interval from 0 to 2 pi, just to make it a little bit simpler. Okay, so on the interval from 0 to pi, we've got a derivative is this purple graph, and all of the derivative values are negative here, right? So that just says the original function is decreasing, and it is. That green function is our original function that's decreasing. And it goes to negative infinity as we approach pi over 2 from the left and the right. And that's consistent with some of our calculations that we did earlier. Now, the slope of this function, of this green function, that's the function we're interested in, seems to be positive as we go from from positive pi over 2 to pi. The function's increasing as we go from left to right. And if we look at the derivative graph, all those slopes are positive, right? Now, it shows us here that they're very, very steep and positive when we're near pi over 2. But then the slopes get less steep and less steep and less steep until they approach this minimum. It looks like the minimum value of our slope is at 3.33, and it occurs at approximately 2.24 as our x value. So at that x value, we've got a minimum slope of that 3.33. And then the slope starts increasing again. They start getting steeper and steeper and steeper as we approach pi. So that's consistent with what we see. Now on this next branch from pi to 3 pi over 2, the green function is decreasing. So all the derivatives should be negative. And if we look at the value of the derivative function, it's always negative here. And we see that these are very large negative slopes as we get close to pi. And then the function gets less and less steep and less steep until at this x value, x equals 4.05 approximately, the slope is a negative 3.33. And then they start getting steeper and steeper and steeper, so increasingly negative slopes. And so the slopes go to negative infinity as we approach 3 pi over 2. And then from 3 pi over 2 to 2 pi, the original function is this green function. It's increasing as we go from 3 pi over 2 to 2 pi. And all the slopes are positive. So we don't have to, but if we wanted to, I always like to do this. We could graph a tangent line. Let's graph y equals f of x naught. And I think I called it f nu because I had f in multiple places. Plus f prime at x naught. And then we multiply by x minus x naught. We add a slider for x naught. Let's let x naught go between, let's just say 0 and 2 pi. And let's plot the point x naught and f of x naught as well. Oops, I want to call that f nu again. So that's our function value. And that white line is the tangent line. And then let's see what happens as we let x naught run from 0 to pi, 0 to 2 pi. So those are our tangent lines. They have positive slope there. They have negative slope there, which is given by those purple values on the y values on that purple graph. They have negative slopes. Now they have positive slopes. The slope values are the y values on that graph. So if we wanted to, while we're plotting this point and its tangent line, maybe we want to look at x naught and then the slope at x naught. This says that the slope at this x value at 0.628 is approximately negative 0.4. And that seems consistent with what we see in this picture. Maybe we can run this a little bit slower. Bless you. So right here, our slope is approximately 3.38. Actually, let's let x go from pi over 2 to pi now. So as I let my x value increase from pi over 2 to pi, see how steep that line is? And it definitely has a positive slope, right? Because it rises as you go from left to right. It rises in a very, very steep way. But as our x value increases, the line still has a positive slope, but it becomes less steep until we get about right there to the minimum value of that derivative. And then as our function, or excuse me, as our x value continues to increase, it starts getting steeper again, right? And then the slope at that point is given by the y value on the purple graph. And so you can do that on each branch. Now on this next branch, the slopes are all negative. We can tell because the function is decreasing. You can also tell if you just let that x naught be an x value in that branch, and then let x just change. X goes from pi to 3 pi over 2. And we can see it starts off very, very steep, but with a negative slope. Then it becomes less steep and less steep and less steep until it gets to a minimum magnitude slope of that 3.33. But then the slope starts getting more and more negative again. So it gets steeper and steeper and steeper. The magnitude gets larger and larger, and we're multiplying by -1. So the slope is actually going to negative infinity there. And then on the next branch, the slope is positive, but then it sort of flattens out. That slope starts to approach 0. So that's what happens. And that pattern repeats itself. So the original graph is that green one, and then the derivative looks like that. Now it's a little bit funny how the Desmos is graphing this. The branches themselves are going to go to negative infinity as we approach those odd multiples of pi over 2, and positive infinity as we approach the odd multiples of pi. And then we get that negative natural log of 2 as the maximum value at all of those even multiples of pi. And maybe let's go from negative 3 pi to 4 pi. That's what we see for our graph. And then the derivative is consistent with what we expect. The derivative is negative, or we can see that the function's decreasing, so the derivatives are negative. The function is increasing, then it reaches a maximum, and then it's decreasing. The derivative is positive, then it's 0, and then it's negative. So the function's increasing when the derivative is positive, it's 0 at that maximum, and then it's decreasing. The function is decreasing when the derivative is negative. On this branch, the slope is positive the whole time, we see that. And then on this branch, the slope is negative the whole time, we see that. And then it just repeats that process over and over again. So it repeats every 2 pi. We see that negative slope, that positive slope, zero slope, and negative slope, and then the positive slope, and then it continues in that way. All right, so that's the derivative. And then we can compute the second derivative using the derivative. So this is our first derivative. In order to take the second derivative, it might be helpful to distribute that cosine of x in the denominator. So I think I'd call that cosine squared x plus cosine of x. That's my first derivative. Same function as before, it's just in a different form. And then if we want to take the second derivative, just use the quotient rule. Actually did this calculation before. So we have according to the quotient rule, the derivative of a quotient is the bottom functions, that's low, d high. Derivative of sine of x is negative, or negative sine of x is negative cosine of x. Minus high, so we're subtracting negative sine of x, so that means we're adding sine of x. D low, that requires the chain rule for the derivative of cosine of x. So we're gonna have 2 times the original function, which is cosine of x, times the derivative of the inside, which is negative sine of x, minus the derivative, well, plus the derivative cosine of x, which is negative sine of x. All divided by low. So that was actually cosine of x times cosine of x plus 1. And then we'll square both factors. Square that factor and square this factor, which is the same as taking that original denominator, or the derivative or denominator for f prime and then squaring it. So that's f double prime. Gives us some indication of the concavity of our function. And we should simplify a little bit. We see that these guys have, when I look at this second set of brackets, I see I've got a negative sine of x here and a negative sine of x here, so I can factor that out. That negative sine of x times the positive sine of x that we had out front would give us a negative sine squared x. So 2 cosine of x times that negative sine of x is the original factor we had there, and then we have a plus 1 here. Don't need those parentheses anymore. I think I'll replace those brackets with parentheses. And then if I distribute this negative cosine of x here and here, I get a negative cosine of x quantity cubed. And then negative cosine of x times negative cosine of x is negative cosine squared x. So that's what we've got. And if we distribute this sine squared x through the parentheses, we'll have 2 sine squared cosine of sine squared x cosine of x. And then I've got a negative sine squared x. And the negative cosine squared minus sine squared is actually negative 1 times the quantity sine squared plus cosine squared. And sine squared plus cosine squared is 1. So it's going to be just a negative 1 term if we combine those. Just trying to think of ways to simplify it. Can't think of anything. Well, actually, I guess we could replace the sine squared with 1 minus cosine squared, right? Then I would have a negative cosine cubed, and then I'll have when I distribute this negative 2 through the parentheses, I'll have negative 2 times cosine of x, and then negative 2 times negative cosine of x, or negative cosine cubed x. Let's try that. Negative times a negative is going to give us a positive 2 times cosine cubed x. And if I've got 2 of those and I'm subtracting 1 of them, that means I only have 1 of them, right? That looks much simpler than it was before. Still not sure how it factors or anything. But let's look at that graph. It says use parentheses around the argument of cosine. Sometimes I just put it on the entire function. That's what the second derivative looks like, if I've simplified everything correctly. Let's get rid of that graph of the function of interest. This suggests that our function has is concave upward whenever the second derivative is positive. So we've got a second derivative that's positive here and negative here. So it should be concave upward on this interval and concave downward on this interval. And at this x value, our original function should have a point of inflection. And the same thing happens here. It's concave upward, then it's a point of inflection, and then concave downward. Now here, the graph of, or the second derivative is negative the entire time. If the second derivative is negative on this entire interval, then the graph would be concave downward on that interval. And then that pattern repeats. Now let's look at the original function. I'm just going to say y equals natural log of the absolute value. Cosine of x divided by cosine of x plus 1. Is that consistent with what we have for that second derivative? I think so. The claim is that the graph is concave upward on here until we get to this x value, and then concave downward the rest of the time. That seems consistent with our picture. Maybe we should just focus on maybe the interval from negative pi over 2 to 3 pi over 2. I just want to do one period at a time. Okay, so we see a little bit of the repetition. We can see where it starts to repeat itself. So the graph is concave upward until we get to this x value at a 3 pi over 4. And then at 3 pi over 4, the graph changes from concave upward to concave downward. And that seems consistent with what we see on the green graph. Or wait, the green graph is the original function, and then this is this teal one is the second derivative. Okay. So second derivative is 0 at this negative 4.04 or 0.5 approximately. So is the graph concave upward there, or concave upward on this side and then concave downward on the other side? No, it looks like it's concave downward on this side and then concave upward on that side. It looks flipped. This is concave downward, and then the branch of the second derivative shows that the second derivative has negative values, so that seems right. But there seems to be something wrong with what I did right here. Must have been a calculation error with that second derivative. Let's do this on paper and take our time and make sure that we sort of cross our T's and dot our I's. Make sure we don't miss anything. And then we'll look at the second derivative. I think I made a calculation error when I tried to take the derivative using the computer, or just by typing it into the computer and then editing in line. All right, I think I just talked about my computation of f double prime without recording. I'm sorry. This is my f prime. I just used the quotient rule, so that's low d high, derivative of negative sine of x is negative cosine of x, minus high, so I'm subtracting a negative sine of x, so I get plus sine of x. D low requires the chain rule. If we think of this as cosine squared x, the derivative is 2 times cosine of x times the derivative of the inside, which is the negative sine of x, plus the derivative of cosine of x. Derivative of cosine of x is negative sine of x. So then if we distribute, cosine times negative cosine is that negative cosine cubed. Cosine times 1 times negative cosine is the negative cosine squared. Then I've got a 2 cosine of x times negative sine of x times positive sine of x is negative 2 cosine of x sine squared x. And that sine times negative sine is negative sine squared. So then we said I've got a cosine squared and a sine squared with the same SIGN sign out front, so I can factor that sine out, and sine squared plus cosine squared is 1. So this piece is 1. That I just brought down, and that I brought down. So I've got this now. And I said I'd really like to write everything in terms of cosine. So I replaced my sine squared with 1 minus cosine squared, because sine squared plus cosine squared is 1. 1 minus cosine squared is the same as sine squared. So I can substitute that in. Then we distributed the 2 cosine of x here and here. I get 2 cosine of x times 1 is just itself. Then 2 cosine of x times negative cosine squared x is negative 2 cosine cubed x. And now I've got a cosine cubed and a negative 2 cosine cubed. So I have 1 minus 2 of those, so that's negative 1 of those. So that's there. And then the 2 cosine of x and the 1 I just bring down. And then if I distribute this negative from outside the parentheses into the parentheses, it just flips all the signs. This is cosine cubed minus 2 cosine of x minus 1 divided by that denominator. And I think we're supposed to divide by low, right? So you're supposed to square both factors in the numerator or in the denominator. I think I forgot to square those. Okay, so this is what I'm going to type into Desmos now, and hopefully I'll have the right SIGN sign. Okay, so when we look at the formula in Desmos, the signs in the numerator were correct, but I forgot to square both factors in the denominator. That cosine should be squared. Now I think we've got the correct second derivative. So at this point, negative 4.05 approximately, the graph changes from, or the second derivative, oops, I'm sorry, I'm looking at the wrong graph. At this point, negative 4 pi divided by 3. Actually, the green graph is the original graph. The teal graph is the second derivative. So the second derivative is 0 at negative 4.05. Second derivative is negative to the left of that. So my original graph should be concave down there. And then the second derivative is right to the right of that is positive. So the original graph should be concave upward there. So let's evaluate at that point of inflection, that negative negative 4.05 approximately. I think I called that F nu. I'm going to take negative 4.046, and I'm going to evaluate F nu there. So graphs seem to go from concave down to concave up. I think it does. And then at this point, at x equals approximately a negative 2.237, the graph goes from concave upward to concave downward because the second derivative goes from positive to 0 to negative. So let's evaluate F nu at that point. That's negative, whoops, negative 2.237 approximately. Is that what it was? We want F nu evaluated there. Let's get rid of that second derivative. Second derivative goes from positive to 0 to negative at that point. I wish I could sort of get those numbers out of the way. Does the graph seem to go from concave upward to 0 to concave downward? It does. So we've got concave down, then the second derivative is 0, and then concave up, 0, that 0 point of inflection, then concave down. That consistent with what we see in the second derivative? It sure is. And then over here, our function it looks like it's concave downward the whole time. So I'm expecting the second derivative values between negative pi over 2 and pi over 2 to all be negative. And they are. And then over here on the interval from pi over 2 to pi, our second derivative is 0 at positive 2.237. So we're starting to repeat that pattern that we saw over here. And at that point, the original graph should be going, or this should be going from concave downward to having a point of inflection to concave upward, because the sign of F double prime changes from negative to 0 to positive. Is that what we see? Concave downward, point of inflection, concave upward? Yeah, that looks right. So I think our second derivative is correct. Then if we look at the first derivative as well, and we can see some of the changes of sign in the first derivative. So the first derivative is negative here, and the function is decreasing. So the original function is the green function. This function is decreasing there when this first derivative is negative. That's good. The slope gets increasingly steep, right? And actually, I want to start at, let's say, negative 2 pi. So if we look at our tangent lines, and we look at the value of that first derivative, so I think I want to get rid of those labels on the points of inflection. I want to keep the points, so I just don't want to label them. Now let's look at the tangent line as we change that x naught value. So we've got a negative slope. It's tiny and negative. So the value of the slope is at negative 0.278. And then as x approaches negative 3 pi over 2, those slopes get larger in magnitude, but increasingly negative. So the tangent line gets steeper and steeper and steeper. And then from negative 3 pi over 2 to pi, the slope flips. It starts becoming positive, right? And so our slope is actually increasing here. It's increasing because it's a negative value, but it's becoming, actually, is that correct? Is our slope increasing or decreasing? No, our slope is positive, and then it's getting less steep. So it's actually decreasing until we get to that point of inflection. Then at the point of inflection, that is the minimum value of that derivative. The function goes from having a positive slope that is getting smaller and smaller. So it's very steep, and then it gets less steep and less steep and less steep until we're at that minimum of the first derivative. That's the point of inflection. That's when the second derivative is 0. And then our slopes start increasing again. And so this tangent line starts getting steeper and steeper and steeper. But if we look at that second derivative at the same time, we can see that that second derivative is 0 there at that x value. And the first derivative has a minimum there. So we graphed f prime at that x value. Do I really want to do that? I think I just want to do it at the point of inflection. So that's the minimum of the first derivative. And it's not exactly right because I was estimating, but I was saying that the second derivative was 0 there. It looks like the second derivative is 0.0018. I was looking for the true 0. It's very close to that negative 4.046. So as we continue to let our tangent line move from branch to branch, we see we've got very large negative slopes, and then those slopes are increasing until we get to a minimum magnitude, maximum slope. No, wait, is that right? No, minimum magnitude slope, but it's negative, right? So it's like actually a maximum when we look at the derivative itself. So the derivative is actually increasing here in this interval, but it's because it's going from a large negative number to a smaller negative number. And the smallest negative number it achieves is at that maximum of the first derivative, which corresponds to a 0 of the second derivative. And we can see that if we evaluate not just f prime, or not just f, but f prime and f double prime at that x value. And we are using purple for f prime. And this teal for f double prime. It's a little busy, the graph is now. But again, notice that the 0 of the second derivative corresponds to a maximum of the first derivative. The original graph is concave up when the second derivative is positive. Concave downward when the second derivative is negative. And that's where the first derivative is increasing. And then it switches from concave up. But when the first derivative is increasing, the original graph is concave upward. And the y values on f double prime are positive. When the original graph is decreasing and concave downward, the first derivative is decreasing and the second derivative is negative. I hope that made sense. I think everything I said was true, but I'm not sure if the ideas were actually connected that time. I'm a little bit tired. But we sort of continue in this way, looking at that tangent line, and then looking at how the values of the second derivative and the first derivative and the original function change. So here our slope is very large and positive. Then our slope decreases until it's 0 at 0. And then our slope continues to decrease. Now our slopes are negative and they get larger and larger in magnitude. Since their slopes are decreasing the whole time, the second derivative is negative the whole time. So the graph is concave downward there, and we can see that with that green graph. That's our original function. It's concave downward the whole time. Then on the next branch, our graph is concave downward when the second derivative is negative and that slope is decreasing. Then at the point of inflection, our slope has a minimum, and then our slope continues to increase. And since our slope is increasing, the graph is concave upward, which is consistent with that value of the second derivative, which is positive. So we can kind of see all of those at the same time if we graph them at the same time. Sometimes you have to be careful though. You have to sort of keep track of which one is which. The green graph is our original function, the purple is our first derivative, and the teal was our second derivative. All right, so that's a lot of information, and we plotted a lot of points. The points kind of make the graph busy. But if you graph those points of inflection, then you can see, and then you graph the first derivative and the original function. You can see when the function is increasing or decreasing based on the values of the original function, or excuse me, the values of the derivative, the purple graph. And you can see when we have a point of inflection whenever the first derivative has a minimum or a maximum. When the slope is decreasing, so when our derivative is decreasing, that means our graph is going to be concave downward. The original function is concave downward. When our slope is increasing, that means the original graph is concave upward. And all of that is consistent with these pictures. I think that graph is pretty cool looking. And you can sort of graph tangent lines, and that kind of helps you get a sense of what's going on as well. Like the derivative graph isn't shown anymore, so we're just seeing that point floating around. That point would have been on the derivative function, the graph of the derivative function. Okay, so that's that. I like this because it shows you sort of how to infer what the graph of that logarithm looks like. And again, we start by graphing the argument. Usually I graph the argument with the absolute value first. And then I say, well, what would happen if I took the absolute value? And then when we take the absolute value, we know we're taking the logarithm of a number that is strictly positive. And we're going to have asymptotes wherever the argument has asymptotes. And we're also going to have asymptotes wherever that argument is approaching 0. And then we can think about the behavior of the original graph as x approaches those asymptote values. And we're going to get positive or negative infinity near the zeros of the argument. And we're going to get positive infinity where our argument goes to positive infinity, because natural log of x goes to positive infinity as x goes to infinity, and natural log of x goes to negative infinity as what's inside goes to 0 from the right. So when we take the log of a tiny positive number, we get a large negative number. So that's what we see here. So we start with that, and then we start examining first and second derivative to look at where the function's increasing or decreasing, concave up and concave down. And we get all these beautiful and interesting features. So we can graph a lot of this by hand, but it's really pretty to see the graphs on desmos.com. Look at the graphing calculator, or let the graphing calculator do most of the work. But we still had to understand calculus, had to understand limits, derivatives, first derivatives, second derivatives, in order to both graph those functions and then interpret them. To come up with the functions in the first place, also the calculations and interpret them.